All right, welcome to AP Chemistry. We're looking at topic 2.6, resonance and formal charge. Our learning objective here is to represent a molecule with a Lewis diagram that accounts for resonance between equivalent structures or that uses formal charge to select between non-equivalent structures. Okay, so anytime we have to represent a molecule, we're going to have to interpret either a a structure or a Lewis diagram that's already drawn, or we're going to have to draw one ourselves. And so we are going to be competing between, or we're going to be looking at resonance structures where we have equivalent structures. All the rules for formal charge are met, and there is not one preferred structure over another. And then we're looking at non-equivalent structures and using rules for formal charge to select between competing structures, as we would say. Okay, so let's go ahead and take us to the information here. And so I'm not going to read all of this in this video, but you should be writing down what are the two main criteria used to determine the most plausible Lewis diagram for a molecule or ion, and how does formal charge specifically help this process. And so what we notice, and for some reason, I don't know why that's happening. All right. Well, that is what it is. There we go. So we'll look at sorry, I got distracted. What are the two main criteria for that? Basically, we're looking at octet rule and formal charge. And so the octet rule is a fundamental principle. We've already talked about that, where atoms tend to gain or lose or share electrons until they are surrounded by 8 valence electrons. In unit 2.5, we talked about how we write Lewis structures according to the octet rule. And then we also talked about the exceptions to the octet rule when we looked at incomplete octets, expanded octets, and then also odd electron species. Formal charge is a hypothetical charge assigned to an atom in a molecule, assuming that electrons in the chemical bond are shared equally between the atoms, regardless of their electronegativity. And we have a calculation for this. And we use formal charge to gauge whether or not to look at competing Lewis structures to see which one is better. And we have a set of rules for that. But before we go into that, let's talk about how we calculate formal charge. And so I have a picture here that shows the formula for formal charge, and it's telling us formal charge is equal to the number of valence electrons minus the number of non-bonding electrons minus 1/2 the number of bonding electrons. And so here I have two structures, structures A and structures B, and we're going to calculate the formal charge of each atom in those structures. And then we're going to apply some rules to determine if structure A or structure B the preferred structure. And I think this will make things very clear for you. So the first thing that we're going to do is look at structure A. And for hydrogen, we notice that hydrogen, if we look at our periodic table, has 1 valence electron. So I'm applying the formula, number of valence electrons. So as let's go ahead and erase that a little bit. Let's put in here formal charge is equal to number of valence electrons minus non-bonding electrons minus 1/2 of bonding electrons. And then let's just put over here hydrogen. So the formal charge of hydrogen is going to be 1 valence electron minus, in this picture, we don't have any lone pair, so the non-bonding electrons is 0 minus 1/2 of the bonding. We recognize that covalent bond represents 2 electrons, so 1/2 of the bonding electrons, which is 2, and 1 minus 1/2 of 2 is 0. So the formal charge of this hydrogen here is 0. We look at the carbon, and the carbon we know has 4 valence electrons. In this picture, we have 0 non-bonding electrons, no lone pair. And so minus 1/2 of 2, 4, 6, 8. And 1/2 of 8 is 4. So 4 minus 4 is 0. So the formal charge of carbon in structure A is 0. Then we look at nitrogen, and nitrogen has 5 valence electrons. Now here we see that this has 2 non-bonding, so we're going to put 2 minus 1/2 of 2, 4, 6. And so 5 minus 2 minus 1/2 of 6, which is 3, is 0. So this also has a formal charge of 0. Now, if we do the same thing for structure B, and I'm going to rewrite the formula here, valence electrons minus non-bonding electrons minus 1/2 of bonding electrons. And so we look at hydrogen. And again, hydrogen meets the same criteria that we saw before. It's 1 minus 0 minus 1/2 of 2. So this is 0. Nitrogen, however, does not have the same calculation because nitrogen has moved to become a central atom. And so nitrogen has 5 valence electron minus 0 non-bonding minus 1/2 of 2, 4, 6, 8. And so 5 minus 4 is 1 or plus 1. So the formal charge of hydrogen is plus 1, 0. Nitrogen is plus 1. And then carbon, as we're going to see, the sum of all the formal charges should add to the to 0 for a neutral molecule, and that's what this is. And so we should see carbon has a formal charge of -1, but let's take a look at it anyway. And so we see it has 4 valence electrons minus 2 non-bonding electrons minus 1/2 of 6, which is 3. So 4 minus 5 gives us not 0. I don't know why I put 0 there. Gives us -1. All right, -1. All right, and so there are our formal charges. That's how we calculate formal charge. It's really that easy. We just did 6 calculations in almost no time. All right, so we're going to go down, and there are some rules that we need to apply to formal charge to help select which is the best structure. And the concept of formal charge is useful because it helps us distinguish between competing skeletal structures or competing resonance structures. So when we calculate formal charge, we have 4 rules that apply. One is that the sum of the formal charges in a neutral molecule must be 0. And so we see in both of these structures A, structures B, those are both neutral molecules. It's both the same compound, just arranged differently in the Lewis structure. However, we see that 0 plus 0 plus 0 equals 0 because HCN is a neutral molecule. We also see that in structure B, hydrogen, nitrogen, carbon, 0 plus 1 minus 1 equals 0. So the sum of the formal charges does equal 0 because those are both neutral molecules. And so that's all rule number 1 is saying. Now, if we had an ion, now the sum of the formal charges must equal the charge of the ion. And we're going to see that take place later on, and we'll see that play out. But it's a very similar rule to rule number 1, except for if we have a charge on this molecule ion, then the formal charges should sum to that charge of that ion. Rule numbers 3 and 4 are really where we're going to spend most of our time as far as distinguishing between our competing skeletal structures. And so we see here that small or 0 formal charges on individual atoms are better than large ones. So if we had 2 structures that we were looking at and we want to decide which one is the best, the one that has the smallest formal charges or 0 formal charges is going to be the best structure. And then there are going to be times, and we're going to see an example of this too, when formal charge cannot be avoided. Negative formal charge should reside on the most electronegative atom. So we're going to make sure we apply that rule. And again, we'll use these rules in some examples so that you are ready for a test. So if we look at the structure A and structure B, which we just drew, what we would see then, and I have this rewritten with the formal charges calculated. What we would see then is we would have to decide which structure is better. Is it structure A or structure B? And so we look at rule number 3, and it says small or zero formal charges on individual atoms are better than large ones. And so we noticed that all of the atoms in structure A have a formal charge of 0, and whereas structure B has 0, plus 1, minus 1, 0 would be preferred over charges. So structure A, according to rule number 3, would be the best structure out of those. So the two competing structures, structure A, structure B, we would choose structure A based off of rule number 3. All right. We also see in structure B that carbon, the least electronegative atom, has a negative charge, and nitrogen, the most electronegative atom, has a positive charge. That would be another way of eliminating it, but we eliminated based off of the magnitude of the formal charges. 0 is preferred over the plus and minus ones. All right, so we're going to look at another one. We got which resonance structure is likely to contribute to the most correct structure. Again, we're going to apply our rules for formal charge, rules 1, 2, 3, and 4. Obviously, none of these molecules have a charge, so they are not ions. So the sum of the formal charges should equal 0 in every one of those. And then we're going to be looking for small or 0 formal charges, which would be better than large ones. And then we're going to look for formal charges that are negative, if they cannot be avoided, to be residing on the most electronegative atom. Okay, so in A, okay, this is going to require us to perform formal charge calculations. Now we have to go back to our formula. Formal charge is equal to number of valence electrons minus non-bonding electrons minus 1/2 of bonding electrons. And so in structure A, that's what we're looking at here, we're going to see, and let's read these left to right. So meaning the first one that I list is going to be the nitrogen on the left. So nitrogen, and I could label it nitrogen L or nitrogen center or nitrogen whatever, but I'm just going to read these left to right. And so nitrogen has 5 valence electrons minus 2, 4 non-bonding minus 1/2 of 2, 4. And so we see 5 minus 4, which is 1, minus 1/2 of 4, which is 2. So this is going to be -1. So -1. All right. So 1 minus 2, which is -1. All right. So then we're going to go to our second nitrogen. And this second nitrogen has 5 valence electrons. All of them do. And then we have 0 non-bonding. We see no lone pair on there. Minus 1/2 of 8. And 1/2 of 8 is 4. So 5 minus 4 is going to be +1. So this is going to be +1. Now we follow rule number 1. We know that the sum of the formal charges must equal 0. This means this oxygen must have a formal charge of 0 if that's going to be true, but we can still calculate it. And we see that we have 6 valence electrons minus 2, 4 non-bonding minus 1/2 of 4. So 6 minus 4 minus 2, which is indeed 0. And so for structure A, we see our formal charges are -1, +1, and 0. Then we have to look at the formal charges of structure B, because we cannot decide based off of the formal charges of just one molecule. We have to look at all of them and see which one follows those rules a little bit better. So we're going to go ahead and write the formal charge. Again, just to make sure I'm following the formula, minus the non-bonding electrons minus 1/2 of bonding. And we should always be committed to writing these things. Again, I'm going to read this left to right. So this first nitrogen is going to show 5 valence electrons minus 2 non-bonding minus 1/2 of 6. And so we see 5 minus 2 minus 3, which is 0. So this has a formal charge of 0. This second nitrogen is no different than the nitrogen that we saw over here. We see that we have 5 minus 0 minus 1/2 of 8 and this is going to end up being +1. So according to our rules, what would be the formal charge of oxygen? That's right, it would be -1 because the sum of the formal charges should equal 0. But we'll go ahead and calculate it anyway. 6 minus 6 minus 1/2 of 2, which is equal to -1. And so we show those, and we go to our third structure, C. And in our third structure, once again, I'm writing the formal charge calculation. And so we see formal charge is equal to the number of valence electrons minus non-bonding electrons minus 1/2 of bonding electrons. If you can read that, that's kind of terrible. So we're reading these left to right again. Nitrogen, 2, 4, 6. So first of all, it has 5 valence electrons minus 6 non-bonding electrons minus 1/2 of 2. So 5 minus 6 is -1 minus another 1. This is -2. So this is -2. Again, this nitrogen in the middle is the same. It's been the same. It's 5 minus 0 non-bonding electrons minus 1/2 of 8. And that's going to be +1. So this is +1. And then what we notice is if the sum of the charges is going to be 0, well, then oxygen must also be +1. But let's go ahead and calculate it. 6 minus 2 minus 1/2 of 6. So 6 minus 2 minus 3. So 6 minus 5 is +1. And hopefully you can see that. +1 plus 1 minus 2. All right. And so now we have the formal charges of structure A, B, and C. And our job is to determine, are these equivalent structures, or is one preferred over another? And we do that by looking at our rules for formal charge. And so we remember that the sum of the formal charges in a neutral molecule must be 0. All of them meet that criteria. Usually you're not going to eliminate one over the other based off of that. But you will in rule number 3 and 4. So in rule number 3, it says small or 0 formal charges on individual atoms are better than large ones. So we can see that in structure C that we see a -2 and a +1 and a +1. All of these have some numerical value other than 0. So the magnitude of the formal charges is greater in C. And so that would not be preferred. And we would eliminate C as being a preferred structure based off of rule number 3. Now, when we get to look at structure A and B, they both have +1, -1s, and 0s. So we can't use rule number 3 to determine which structure is better. So we're going to look at rule number 4. And rule number 4 says when formal charge cannot be avoided, and it couldn't, negative formal charge should reside on the most electronegative atom. The most electronegative atom in this molecule is oxygen. And we see in structure B that oxygen has the negative formal charge. Therefore, structure B would be preferred and structure A would not be as good. And so we can see that we would choose structure B as our preferred structure. And that's how we use formal charge to distinguish between competing Lewis structures. All right, so we showed 2 examples, one with structure A and structure B over here, and then we have those with N2O, A, B, and C, 3 different Lewis structures there, which gave us the best arrangement. It was structure B. Okay, so if we were drawing N2O, we might draw it 3 different ways. Which way is going to be the best? The one that meets the criteria for formal charge rules. All right, then we get into resonance. And resonance is looking at equivalent structures. And so what is resonance in the context of Lewis structures, and why is it considered a refinement? I'll let you read through that and answer your question there. But the concept of resonance occurs, I do want to spend time here, when more than one valid and often equivalent Lewis structure can be drawn for a molecule or ion. So differing only in the placement of electrons, specifically pi electrons in multiple bonds. So we remember that those pi electrons are found in double bonds and triple bonds. single bonds only have sigma bonds. And so when such equivalent structures exist, none of them individually provides a complete or accurate representation of the actual bonding. So this is a very key part right here. None of the structures, even though they're equal, will provide an accurate representation. None of them. So what do we have? Why are we drawing structures that we say are equivalent, and yet none of them are accurate of what is actually occurring? Well, it's because it's just a way to represent them. Remember, what we're doing here is we are representing a molecule in the Lewis diagram that accounts between resonance or equivalent structures. In reality, there's some type of hybridization that occurs in the bonding where resonance occurs within a molecule. So instead, the true electronic structure is an average, I like that, average or hybrid of all contributing resonance structures. The molecule does not rapidly switch between these forms. Rather, it exists as a single stable resonance hybrid at all times. So let's talk about this looking at the nitrate ion. All right, and so we're going to do that real quick, or maybe not real quick. And then we'll come back to this bond order definition as we are looking at this nitrate ion, or considering the nitrate ion. So I do like this nitrate ion as an example. One, because it's a polyatomic ion, and it forms covalent bonds between the nitrogen and the oxygen. So what we're going to show is our Lewis structure. We're going to show our framework NO3, and then we're going to do our count, just like we do this by the number. So we have 1 nitrogen times 5 valence electrons, which is 5. We have oxygen, which is 3 times 6 valence electrons, which is 18. And so we end up with 18 plus 5, which is 23 electrons. And you might think, well, do we have an odd electron species here? And the answer is no. If you notice on the nitrate ion, notice there is a charge on there, and that charge is negative, which means that there is an additional electron. And so to our count, we must add 1 more electron. And so we now have 24 electrons. All right, and so now that we have that count, all we have to do is add our electrons. And so we show 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And so we are short because nitrogen does not have an octet, and nitrogen does not form an incomplete octet. So when we have this situation, we have to add a double bond somewhere. And so we can add a double bond in any one of these places. We can show it right there. If we do that, or when we do that, we have to remove electrons so that oxygen will have an octet. And now all atoms have an octet, and there's a total of 24 electrons. Now, because this is an ion, ions are drawn with brackets. And these brackets, we put ions in a bracket, and these brackets have the charge on the outside. And so that would be the appropriate way to represent the nitrate ion. Now, in reality, just redrawing this nitrate ion, we can have, I'm going to draw this first. We can have nitrate with double bond here. All right, let's do that. And we'll show our lone pair. And we can also have let me show that there. And then we have our double arrow. Yeah, and then we can also move nitrogen where we show a double bond down here. And then we could also show, and y'all notice that I am drawing, unfortunately this line's going to get in the way there, and double arrow in between these. So nitrogen, and we'll put our double bond there, oxygen, oxygen, and then we'll show our lone pair. Very hard to show my lone pair right there. All right, and then let's make sure we can see it because it's not good that we can't see it. There we go. We'll just draw around it this time. All right, so there are three competing structures. All right, and all of them are based off of what we saw here. So we can show our calculations for formal charge, and our formal charge shows that, and it doesn't matter which one. If I show the oxygen with a double bond, and I'll put the double bond on this side, we see that it is equal to 6 minus 1/2. Excuse me, that's not true. 6 minus all the non-bonding, which is 6, minus 1/2 of the bonding, which is 2. So 6 minus 6 is 0, minus 1/2 of 2 is -1. So this would be -1. We see the other oxygens. I did something wrong there. I did something very wrong on my picture. So I got to fix it. I shouldn't have drawn this pair in there because it are 2, 4, 6, 8 on oxygen. I wasn't paying attention to when I drew it. So I'm going to have to redo my formal charge calculation. This is going to actually be 6 minus 4 non-bonding electrons minus 1/2 of 4. So 6 minus 4 minus 1/2 of 4 is equal to 0. All right. And then we have our single bonded oxygen. I'm just showing that line there. Is 6 minus 6 minus 1/2 of 2. So 6 minus 6 is 0, minus 1/2 of 2 is -1. So this one is -1. And then this one meets the same criteria. So then we have nitrogen. By the way, where does it have to be? We know that this is going to be -1. All right. And so, and I need to fix my thing here. This one shows 0 now, as it should. So we're at 0, -1, -1. And so that means nitrogen should have a +1 charge if all of these are going to sum to the charge of the ion. But here is nitrogen. We have 5 minus 0 minus 1/2 of 8. And sure enough, it is +1. And so we notice that if we follow the same pattern, this double bonded oxygen is going to be 0. These oxygens are going to be -1, and nitrogen is going to be +1. +1. This one would be 0, -1, -1. So there is not one structure out of these that is better than the other. And so we would say these are equivalent structures. And what did we do to achieve these equivalent structures? Just like we read a second ago, we moved the pi bond. So notice the pi bond here in this first structure is on the left. Now the pi bond is over here on the bottom. Now the pi bond is over here on the right. And so all we did was move the pi bond in the structure. And what that reading said was, it's not like these molecules just shift this pi bond around. In reality, that does not occur. And as a matter of fact, zero of these molecules, or 0 of these representations are match what we see in reality. In reality, there's some form of a hybridization that occurs within those molecules. And this is where we're going to go back and talk about bond order real quick. So when we look at the bond order of the molecules, the bond order, and we've probably covered this already in your class, but we look at single bonds, and single bonds consist of 1 sigma bond. The bond order is 1. All right. In a double bond, consists of a sigma and a pi bond. The bond order is 2. And in a triple bond, it consists of 1 sigma and 2 pi bonds. The bond order is 3. And so these are pretty easy to determine. And so if we look at, and we're going to just use one of our first molecule, we see this double bond, and we would say, oh, that's easy. The bond order is 2. And we would say this single bond, the bond order is 1, and we would say this single bond, the bond order is 1. However, we already discussed that we already discussed that. Let me go back to this part right here. That instead, true electronic structure is an average or hybrid of all contributing resonance structures. The molecules do not rapidly switch between these forms. And so these bond orders that we show, they don't exactly exist like that. There's some type of average that occurs with that. And so where we see resonance displayed, we have to use a formula to determine the bond order so that we get an average of those bond orders. And so what we're looking at then is the bond order is the sum of the bond orders in all contributing structures divided by the number of contributing structures. So instead of the bond order being 2, 1, and 1, we use our formula and we say the bond order, BO, is equal to the sum of these bond orders, 2 plus 1 plus 1, which would be 4, divided by 3 regions. So notice when we count our values, we got that from 3 different areas. So 4 divided by 3, and what we end up with is 1.33. So instead of these actually having a bond order of 2, a bond order of 1, and a bond order of 1, we actually, as the reading says, have an average. And so this actually doesn't look like a double bond. What it is some type of hybrid double bond, but that occurs in all of these. And so one of these areas is not stronger, does not have more attraction, or it's not a stronger bond, and it is not a longer or shorter bond. They are all equal. They are all of equal length and strength, but that is all based off of an average of the overall bond orders. And so we would say the bond order that exists in every one of these is 1.33. And before we did the average, we said we had a region where there was a bond order of 2 and 1 and 1, and so we could see the bond order was greater in one region of the molecule, where in fact it is equal throughout. All right, and so that's what that reading tells us. And so when we look at these resonance structures, what we read was that none of these match reality. In reality, it is some type of average that we take. We're getting that average from that formula that we just got. And so we see that the strength of the bond are equal in all regions where resonance takes place, and then also the length of the bond. All right. And so that is the main idea for resonance hybridization. And so then we look at another example real quick, and we're going to see in this some resonance as well. So in this one, we see CH3NO2, which is called nitromethane. The first thing we do is we draw a Lewis structure, or we draw the framework, not just the Lewis structure or diagram, but the framework, and we see CH3. So we're going to show all of those. And then this bonded to a nitrogen, bonded to an oxygen, and an oxygen. Let's say that. All right. And so what we see here is that we need to do a count. So we have hydrogen. There are 1, 2, 3. And they have 1 valence electron for a total of 3. We have carbon, which has 1 times 4 valence electrons. That's 4. We have nitrogen, which is 1 times 5 valence electron, which is 5. And then we have oxygen, which is 2, because there's 2 oxygens, times 6 valence electrons, which is 12. All right. And so we see 7 plus 5 is 12 plus 12. So we get a total of 24 electrons. So we're going to distribute our lone pair of electrons until we get to 24. Obviously, we do not put lone pair on hydrogens because they are satisfied with the duet. So we have 2, 4, 6, 8. And then we go to oxygen 10, 12, 14, 16, 18, 20, 22. Whoopsies, nitrogen does not get the octet. So we have a problem. And so the problem would be that we're short electrons. So what we can do is we can add a double bond in one region. And it doesn't matter whether it's here or here, but we're going to remove the double bond, or we'll put the double bond in and then remove some valence electrons so that oxygen has an octet and now nitrogen has an octet as well. So we recount to make sure we're at 24, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and we have 24 electrons there. Now, this is not an ion, so I'm not putting brackets around it. Notice it does not have a charge. However, this does display resonance. And so we can see that because the double bond could be here or here, we're going to draw it two different ways. But which of those occurs? Which of those matches what we observe? And the answer is none, because they are both not good models. All right, so we're going to put those in there. And then we're going to show our double arrow showing that this displays resonance, CH3. And I'm just redrawing what I already drew over here just to make sure that I can show that it does indeed show resonance. And we show the double bond on the bottom now. And then we show the single bond on the top. All right. So if we looked at formal charge of all of the atoms, we're going to see that indeed these are non-competing structures. But let's go ahead and show it. So for carbon, we see, well, let's see, for hydrogen, having issues there. All right, so for hydrogen, we have, let's see if I can get that to work. All right, there we go. We have hydrogen. We have one valence electron minus 0 non-bonding electrons minus 1/2 of 2. So this is going to be 0. All right, so this is 0, 0, 0. Carbon is equal to 4 minus 0 minus 1/2 of 8, which is 0. And then we have nitrogen, which is equal to 5 minus 0 minus 1/2 of 8, which is equal to plus 1. So this is plus 1. That's going to be the same thing there. 0, 0, 0, 0. And then we have oxygen with the double bond, which is equal to 6 minus 4 non-bonding electrons minus 1/2 of 4, which is 0. So this has a formal charge of 0. Because these are neutral molecules, this has a 0. This one must be minus 1. All right. So we see that they both have meet the same criteria for formal charge. The only difference is that the pi bond moved in shifting from one oxygen to another, or it's just rearranged. So which one of these exists in reality? And that answer is none. Now, it is important to note that we only will use this formula for determining the average bond order, or the bond order, where resonance occurs. So that's very important to recognize. We notice that in this molecule, resonance does not occur between carbon and hydrogen, carbon and hydrogen, carbon and hydrogen, and carbon and nitrogen. Resonance occurs only between the nitrogens and the oxygens. So when we look at the hybridization is only going to occur in this region. The bond orders are going to remain constant elsewhere. So the bond order here, because it's a single bond, is, maybe I'll get a better marker. The bond order here is 1. Bond order here is 1. The bond order here is 1. And the bond order here is 1. But those areas are not displaying resonance. And so they are not placed in our calculation. So we will look at the bond order here, and we say the bond order is 2, and here the bond order is 1. But again, we know that none of these exist. And so we have to take those values, and we say the bond order. Let's see if my pen will work. All right, maybe not. The bond order is equal to the sum 2 plus 1, 3, over how many regions there? And that would be 2. So the bond order is equal to 1.5. So these don't actually exist. What actually exists is something like this. So we show that we have a single bond, ... that dash is showing some type of hybridization of a double bond. And so both of them have a bond order of 1.5. In both regions right here, the bond length and strength is an average of what we would have had. And so they are of equal strength and length, at least in this region. Notice that we did not use these areas where hybridization or resonance does not occur to develop the overall bond order. And so that's just something to pay attention to. I think we went over everything that we should have went over. We're going to go over the objectives again, maybe, if we can find where that is. Let's see. Maybe I need to scroll up or not. Okay, we won't worry about it then. All right. I don't know where it went. All right, so something happened to my screen. Well, it was a good time for it to happen. Well, for now, thank you for watching. Please like and subscribe.